Hello there. We've been looking at dynamic response of multi-degree of freedom systems, and in the last lecture we solved one particular problem, and I highlighted certain useful facts about the mode superposition method. For example, we actually solved an undamped problem, because I still haven't looked at damping in its entirety, although somewhere along the way I have always said that you can incorporate damping this way. Okay? And one of the things that we solved the mode superposition method was that you did not need to consider all modes to get responses. Okay? And secondly, for displacement responses you needed fewer modes to be considered than if they were for forced responses. Okay? So, this is in a sense your basic. Now, how many modes should we consider? Now, this is a very difficult problem to answer. I will answer it later when we take the specific case of earthquake response analysis. The reason behind that is that in earthquake response analysis we can actually identify a parameter which you can get for every mode, and then when you add up the parameter you can pretty much decide how many modes you should consider to get a very good estimate of the force responses. But how many modes should you consider? Well, you really can't tell. Well, the best way to do is try out 5 modes, try out 6 modes, and see how it works. That is not a solution. In general loading, it is very difficult to identify how many modes to consider for force responses and how many modes to consider for displacement responses. Okay. Today, what I am going to do is I am going to go back to damping, and I am going to look at damping for multi-degree of freedom structures. You see, we talked about the fact that if I include damping, now you have this situation. You have a situation where you have the equation which looks like this. Sorry. By now, this and this is something that we know how to get. Today, in this lecture, I am going to concentrate on this. First question is, do I need to get C? When do I need to get C? These are some of the questions that I am going to be asking, okay, and answering, more importantly answering. Asking questions is always such a good idea, but getting answers to them is a far superior concept. Okay. So, let us see. What did we do? We talked about mode superposition. And the point that I make is the following, that as long as you know omega n and phi n, okay, if you know this, the mode superposition method is the only way to go. Even if you do not know this, okay, it is a far superior computationally to go through this rather than solve this equation directly. I have shown you how to solve, and we will go back to looking at it, how to solve this equation. But mode superposition, how does mode superposition look? It looks like this. Sorry, omega n squared mn, okay, for undamped. And this comes from the fact that this, right, the phi n are mass and stiffness orthogonal. That is why I get this equation. Okay. And I said that the corresponding damped system with an equivalence from the single degree of freedom system would look like this. This is what a damped would look like, and we also said that look, so all we need to do is, along with omega n phi n for mode superposition method, all we need to do is define this parameter. Okay. So, if we define the xi in n, and we also talked about the fact that look, since I do not know, I will take that every mode has the same damping, because you remember, we had discussed this, that if a structure is made of the same material, then damping is obtained numerically, and it is the same irrespective of whether the structure is a stiff structure or a flexible structure. Damping pretty much remains the same. So, we can just extrapolate that and say that look, I am going to do omega n phi n, and I am going to define xi. If you are using mode superposition, this is all. If you are using the mode superposition method, that is all you need to do, because why? Then you have and this is your standard single degree of freedom problem, and you can always get y n of t. And once you get y n of t, v of t is equal to phi n y n of t summation, okay, or which we saw was equal to phi into y, all of those things, n going from 1 to n, okay, and we've done it. We've considered damping. Trivial, absolutely trivial to consider damping in this particular manner. Okay. Now, the question becomes that, well, that is it, mode superposition. But suppose you have a situation, and this is equally. So, linear system, okay, superposition method, xi in each mode, no need to define C matrix at all. Since it is a linear system, mode superposition, you define xi in every mode, you do not need to define C at all. Where do you need to define C? If your system is going nonlinear. And you see, a system does not go nonlinear straight away. Okay? A system does not go nonlinear straight away. When you have a, let us say, you have a loading, you have loading, you are loading the structure. Okay? If you look at K, P versus let us say P, how does it go? It actually stays straight, and then it goes nonlinear or something of that sort, nonlinear this way or this way, whatever. This is the nonlinear part, this is the linear part. Now, the question becomes that, look, even in the linear part, okay, you might as well use mode superposition. Only when you go nonlinear do you need to use direct methods, where direct methods are based on mv cv dot plus kv is equal to p. Okay. So, that is when that is the only time I cannot use mode superposition, purely because it is you can't use mode superposition. Mode superposition is only valid for linear systems. So, that is when I need to solve this. And the problem is how do I get C when I have nonlinear? I need to have a C which is consistent with my definition that I have used in the linear part, mode superposition. In mode superposition, what did I say? I said, well, take xi in all the modes that I am going to consider, and that then my C matrix has to be consistent with that, because let us put it this way, since you have linear, nonlinear, at least in the linear part, this solution has to be consistent with the mode superposition method. You understand my point? So, therefore, that is where you have a situation where you need to define C such that C is such that phi transpose C phi, this is n by n, n by n, n by n, is diagonal matrix. So that we get m n plus c n plus k n is equal to p n. Note that k n is equal to omega n squared. So, it is the same thing, and the c n is this one. So, in other words, C n is equal to phi n transpose C phi n, and phi n transpose C phi m is equal to 0. In other words, it is also damping orthogonal. So, that means it is orthogonal with respect to the damping. Remember, we already showed that it is orthogonal with respect to mass matrix, it is orthogonal with respect to stiffness matrix. Now, we are saying that for us to ensure this, which is the uncoupled modal equation, modal amplitude equation, we have to have the damping matrix also, the mode shape vector also orthogonal with respect to the damping matrix. Now, this is a requirement. Okay? This is a requirement, and this is called orthogonal damping, or as I said, remember, when is the now these don't the phi and omega are for undamped systems. Okay? So, it is only m and k that come into picture. So, therefore, nowhere does phi n have to satisfy C. It is just that for us to make it to us to ensure that we get uncoupled modal equations, we need it to be orthogonal. So, therefore, C matrix has to be of a form such that so, once we have that, we see that look, remember we said that C can be of the form, this form, C can be of the form, its mass orthogonal, yes, its stiffness orthogonal. We know that if this is this, then we have the situation where it is a linear combination of mass and stiffness proportional. Okay. So, these are what are known as proportional C matrices. If these are there, then this automatically is satisfied, automatically, because we know that phi is mass orthogonal, stiffness orthogonal. So, if they are of this form, we know that this is true. There is another. Remember, we said that there is a general orthogonality, and I remember I wrote down the form of the general orthogonality. That it was the mass matrices were orthogonal with respect to this also. So, I can actually write down another, this is known as mass proportional, stiffness proportional, this is known as Rayleigh damping, okay. And we have another C matrix which would ensure another C matrix which would ensure this, and that C matrix is of this form. If C is of this form, it is also proportional, because this is, we have shown that this is proportional. Okay? I mean, in other words, that this is the orthogonality, the orthogonality condition of this we have shown. So, if it is a linear combination of all of these, automatically C is also orthogonal. Okay? I mean, the mode shape vectors are orthogonal with respect to the C matrix. Okay? So, let us look at what happens. Note that the only thing is we can always find out the C matrix if we can find out alpha and beta here, and in a more general sense the AB. Okay. So, if we can find that out, we have got a C matrix which is consistent with our whatever we have assumed. Okay. So, let us see what happens when C is equal to alpha m. Okay. So, let us look at this. We have a situation where I am post multiplying and pre multiplying both sides by phi n transpose, post multiplying with phi n and pre multiplying with phi n transpose. So, I have done both. Okay. So, this is equal to C n is equal to alpha m n. Okay. And note that C n is equal to 2 xi n omega n C n, which is equal to m n, which is equal to alpha m n. So, this implies that alpha is equal to 2 xi n omega n. Note something very interesting, and that is that there is only one alpha. So, for it to be case, there is only one for which it will be valid, and so therefore, if I were to look at it, I could say this, that psi 1 is equal to alpha is equal to 2 xi omega 1. If I say this, note that this defines alpha, because I am saying that, look, in the first mode first mode, this is xi. If I put that in, this becomes alpha becomes a unique number. Now, if I were to look at some other, so this is equal to this. So, if I look at it, what would be my xi n in another mode? Well, let us see. Alpha is equal to 2 xi. Okay, so it would become then alpha, I will put 2 xi omega n, 2 and 2 cancel, and xi n would become xi omega 1 upon omega n. Note something very interesting. What form does this take? If I note, let's look at this. This is a very interesting point. The interesting point is the following. I have omega n and I have xi. Suppose I have omega 1 and I fix xi for that value. Okay. So, I have it here. Now, if you look at this, now once you fixed alpha is given. So, therefore, xi n is equal to xi, which is this value omega 1 upon omega n. So, if I were to look at omega 2, what would that be? That would be, look at this would be less, right. So, and how would that go? If I were to look at omega n, this would become like, so omega n over here. Okay. So, let us say that omega 2 is twice. So, if I do omega twice, then xi n is half. Okay. If you look at this, this is a constant. So, this is like xi n is inversely proportional to, so if I look at it, it will be going like this. It is a hyperbola. So, mass proportional damping, what does it do? We know that these have to be here, but if I take mass proportional, this is where I know all modes have to have 5%, but once I make it mass proportional, okay, damping, it underestimates damping in higher modes. And once it underestimates damping in higher modes, what happens? If I take mass proportional damping, it overestimates the contribution of higher modes to response. Understand that if you underestimate response, what are you doing? Lower damping, what does it do? It always increases the accepting for, remember, intransmissibility. Intransmissibility, actually you want to be damping. But let us not go there, that is a design. Let us take a structure. A structure is being subjected to arbitrary loading. I assume damping to be mass proportional. If I assume damping to be mass proportional, I can only fix it in one mode, and that typically is the fundamental mode, because that has the largest value. So, I fix it there. Then what happens to all the higher modes? I underestimate the damping in the higher modes, because it is supposed to be 5%, but actually I take it as 1%, 2%. What happens? I overestimate the contribution of those modes to a response, right, because I have to take xi n has to be lower and lower. So, actually I am actually adding more of the higher modes than necessary. That is a problem with mass proportional damping. Let us see what happens when I have stiffness proportional damping. If I have stiffness proportional damping, let's see. C is equal to beta k. So, if I look at it, let us go through it. This is pre-multiply and post multiply by, so this becomes phi n transpose k phi n, and so this by definition is 2 xi n omega n m n is equal to beta, and what is this? This is equal to omega n squared m n. So, m n cancel out, and what do I get? I get beta is equal to 2 xi n upon omega n. What does that mean? Again, beta is one value, so I can fix it in 1. So, I can say that, look, I am going to say that beta is equal to 2 xi upon omega 1. Once I have that, so that means this is equal to 2 xi upon omega 1 is equal to 2 xi n upon omega n, and therefore, xi n in all the higher modes is going to be equal to xi upon omega 1, which is a constant, into omega n. So, if you look at it, if I were to plot xi n with omega n and I fix it to this, what happens? It goes up in a linear fashion. So, that means the second mode, if this is what is supposed to be, it is actually this. Overestimate damping, and therefore, underestimate in higher modes, and therefore, underestimate response contribution of higher modes. You see, so therefore, it becomes very interesting. If you have mass proportional, okay, you are overestimating the response of the higher modes, overestimating the contribution of the higher modes, okay, while because you are underestimating the damping. If you are stiffness proportional, you are overestimating the damping in the higher modes, and therefore, you are underestimating the contribution of the higher modes. So, now let us look at Rayleigh damping. Rayleigh damping should solve that problem, right, because it is a linear combination of the two. So, let us see what happens. Phi n transpose C phi n is equal to alpha into phi n transpose m phi n plus beta into phi n transpose k phi n. Okay. So, now, if I will do this, this is equal to 2 xi n omega n m n is equal to alpha m n plus beta omega n squared m n. So, let us get rid of it. What we get is 2 xi n omega n is equal to alpha plus beta omega n squared. There are two parameters. To get two parameters, what can I do? I can fix the damping in two modes. So, therefore, what I will do is, let us see what I am going to do. Let me assume that I fix damping in two modes. So, I say 2 xi omega 1 is equal to alpha plus beta omega 1 squared, and I am going to say 2 xi omega 2 is equal to alpha plus beta omega squared. These are two modes. So, let us see what happens. Okay. And I am going to take this thing out, and I am going to take the 2 out. So, what do I get? I get the following. This is implies that I have 2 xi, okay, 1 upon omega 1, 1 upon omega 2, alpha beta. Note that the first equation is 2 xi is equal to alpha upon omega 1, I am put alpha here, plus beta into omega 1, that is this equation. The bottom equation is 2 times I is equal to 1 upon omega 2 alpha plus beta omega. So, I am just take over here. So, this becomes then that I can find out xi xi. So, I can actually take xi xi. So, I can put it 1 and 1. I can put 1 upon 2 xi here, 1 upon omega 1, sorry omega 1, 1 upon omega 2, alpha beta. I can solve for alpha and beta from here. Okay, so, I can solve for it. So, what have I done? Let's look at it. Let's look at it. When I put this and I draw omega n versus xi n, what have I done? I have fixed it here, I have fixed it omega 1 and I have fixed omega 2. So, I have fixed these two. So, how does it actually go? If I were to draw this, okay, initially the mass proportional damping starts thing, and then you see, because higher modes the mass proportional contribution goes down and only the stiffness proportional damping remains. So, Rayleigh damping, if omega 1 and omega 2 are fixed, what happens? We still overestimate. See, omega 1 and omega 2 are fixed, no problem, xi and xi are there, overestimates xi of higher, xi n of higher modes. So, this is like omega 3, it overestimates, right. This is supposed to be the value, this higher modes, underestimates modal response in higher modes. So, in other words, in this process, what are we doing? If we do this, now there is another option. The other option is instead of omega 2, you do some other omega n. But then what happens is, if you fix this and you fix this, all that happens is that it underestimates the middle ones and overestimates the higher ones. Okay. So, you may say that look, I am underestimating a few, overestimating a few, which is why actually in a way Rayleigh damping has been used for so long. The reason Rayleigh damping has been used is that instead of omega 1 and omega 2, you actually take omega 1 and omega m. The ones, omega m is not really omega m, actually this m is approximately about half of all modes that contribute. Because then what happens is, if you take that mode, let's say 4 modes contribute and I take omega 3. Okay, if I take omega 3, what's happening is omega 1 and omega 3 are at 5%. Omega 2 is the damping is underestimated, so its contribution is overestimated. And then the higher modes, omega 4 and all, there is damping is overestimated, and therefore you underestimate their response. But that's okay. In some way people are saying that you underestimate 1 or 2 modes and you overestimate some 4 or 5 modes. In a way, the total response, if you put it together, it sounds good. In essence, it sounds very good. In reality, see, what are we trying to do? You have to understand again that I am trying to see that if I use what is known as the direct integration procedure, which is m plus mv double dot plus cv dot plus kv is equal to p, I can solve that equation, okay, using the direct integration procedure that I established for a single degree of freedom. Go back, all it will happen is instead of a single equation, we will get a set of simultaneous equations which you have to solve for. Does not matter. Direct integration is m v double dot plus c v dot plus k v is equal to p. We solve it directly. This response for a linear system has to be identical to the response where we assume xi in every mode. Okay. So, these two have to give the same answer. So, you have to have a C which kind of gives similar results, and that is what we are saying, that if you do some omega m where m is half of all the modes you consider, you underestimate a few, you overestimate the others, and you say that it acts. But note that the higher modes responses are typically lower. Okay. So, when you are underestimating some modes, you are actually boosting up the middle ones, which you will see that in reality your response to the direct integration procedure will turn out to be slightly more than that from the modal integration, if you use Rayleigh damping. Okay. If you use mass proportional, stiffness proportional, is a disaster, because you can only fix it in one mode, you always fix it in the fundamental mode. So, either you hugely overestimate, hugely underestimate. Okay, Rayleigh damping, at least it logically seems to make sense, but I just told you that underestimating some, overestimating others, when you are overestimating the lower modes and underestimating the higher modes, it does not help. They do not balance each other out, because each mode contributes differently. Okay. So, how do I solve this particular problem? The problem is by considering C to be given as, let us say, I am going to say B going from 0 to n. I consider n series. Remember that this goes from minus infinity to infinity, but I will consider only n of those, and I will say that, look, A B m inverse k into B. If I take this, note what happens. This procedure was developed by Cauchy, and that is why it is called Cauchy damping. Rayleigh damping, 2 modes, Cauchy damping, n modes. Okay. So, how many unknowns do I have? If you look at it, sorry, this is n minus 1, because 0 is also there. So, this n minus 1. So, you have n unknown ABs. Okay. Now, in principle this looks beautiful, because I can fix n modes. Okay. I have only to define n xis, okay, and I am done. Okay. But how do I get the ABs? And that is the question that comes up. Okay. So, let us see. I know that if I were to take this, so this in a sense, if you look at it, basically becomes the following. C becomes equal to A0 m plus A1 k plus A2 m inverse k m inverse k, and so on and so forth. Okay. So, this becomes my solution space. Okay. So, let us see what happens in such a situation. Well, if I were to make it phi n transpose C phi n, I get A0 phi n transpose m phi n plus A1 phi n transpose k phi n plus A2 m into m inverse, which is I. So, this becomes k m inverse k phi n transpose plus blah blah blah. Okay. So, what does this become? This becomes 2 psi n omega n mn is equal to A0 mn plus A1. This I know is omega n squared mn. What is this? Let us see what this one is equal to. Let us see what this one is equal to. Now, if I look at this, phi n transpose k m inverse k phi n is equal to phi n transpose k m inverse into omega n squared m phi n. So, if I put omega n outside, what do I get? Omega n squared phi n transpose k m into m inverse is this. So, this is this. So, this is equal to omega n fourth m n. So, if we look at it, so this becomes a squared omega n fourth m n, and in this way actually you can show that this is equal to omega n sixth m n and so on and so forth. So, now the number of, and this goes up to a n minus 1. Okay. So, that what does it become? It becomes a n minus 1 omega n twice n minus 1 into m n. This is what we get. Okay. So, now if I were to plot this, I have how many? I have n number of unknowns. So, I have to specify in n of those. So, if I specify in n of those, what do I get? I get the following, and I am going to take the omega n this way, okay, so that I get it equal to the following: 2 xi 1 1 up to 1 n modes, okay, is equal to, let us see, A0, A1, A2 all the way up to A n minus 1. And what are the values? This is 1 upon omega 1, the first mode, omega 1, omega 1 cubed, so on and so forth, up to omega 1 to n minus 3. Okay? So, similarly, I can put, and same way, and if I look at the omega nth term, it will be like this: omega n squared, and that is my a n is going to be equal to omega n to n minus 1. Now, note that this matrix I know, because I know all omegas, omega up to omega n, I know this. So, this is a known matrix, known. This is known, given. This is known. This is unknown. So, what is this? This is actually n simultaneous equations to solve for A B. Once I solve for that, okay, once I solve for that, I have got my equation, because C is equal to summation B going from 0 to n minus 1 A B m into m inverse k to the power of B. I found out my A B, I can find out my C matrix. The advantage of the Cauchy series is the following, that once you have the Cauchy series, Okay, if I were to plot my since I have forced all of them will be. So, Cauchy damping, all modes xi, accurate estimates of all modes, and therefore, the ultimate thing is that if you use Cauchy damping, so finally, let us draw the final conclusion from the damping is that, and that is it's very otherwise it becomes very complicated. I have two approaches, M V double dot C V dot plus K V is equal to P, and this is direct integration. Okay? I mean, so I have a linear system. This is the direct integration procedure. Okay? Just please understand that the direct integration procedure is exactly the same as what I'm not going to repeat it. It's exactly the same as what we have developed. Remember that time step, well, instead of a single value, we always say vector. Okay, that's all. So, it just becomes a simultaneous equation. Okay, and the other is the Mn Yn double dot plus 2 xi omega n Yn dot plus omega n squared Pn, and then saying that V is equal to summation n going from 1 to n of phi n Yn of t, which is mode superposition. If we use Cauchy damping, where we enforce that xi is the same in every, these two methods will give if Cauchy damping. Let me just write it down again. Cauchy damping, identical response. Okay? If you use mass proportional, if you use stiffness proportional, if you use any or Rayleigh damping, you are not going to get the same between the two, because if you use mass proportional damping, it will overestimate the response from the higher modes, and so therefore, this one will give, since it overestimates the response, this one will be typically higher than what you get from here. If you use stiffness proportional, you overestimate the damping, and so you underestimate the response. So, this one is going to be lower than this. Okay? And if you use Rayleigh damping, well, it becomes a little bit more complicated, but this one and this one are definitely not going to give you the same result, and so only Cauchy damping will give you the same result. Please understand that, so therefore, the concept of all of these, the question of proportional damping and the fact that your C is mass proportional, stiffness proportional, Rayleigh or Cauchy, all is relevant only if you have a system where you require C, which is when you go non-linear. You go linear and then non-linear. Only then do you require this if you are dealing only with a linear system. Understand that. If you are only dealing with a linear system, only linear system, all this discussion that we have had in this lecture on mass proportional, stiffness proportional, all of these are irrelevant. Why? Because you will always use mode superposition, and if you use mode superposition, then this is the problem that you solve. This is the problem that you solve, where you take xi as the same in all the modes. Okay? You take xi as same in all the modes. If the xi is the same in all the modes, then please understand something, that who cares? In a way, you may say that, well, by taking xi, I am assuming Cauchy damping. You can say that, doesn't matter. But you don't have to, you do not have to evaluate A, B. You say that you are considering Cauchy damping, but that is also irrelevant. Who cares? You are solving modal amplitudes and you are assuming xi to be the same in all the modes. This is an assumption. It's an assumption. So, to consider damping, it is not relevant to consider whether it should be mass, Rayleigh, Cauchy. All of these discussions come into picture only when you have to ultimately look at nonlinear response, and you want to ensure that linear and in the linear domain, the two methods give you the same result. That's when all of this thing of Cauchy, Rayleigh, mass, stiffness, proportional damping becomes relevant. If you are only dealing with a linear system, there is no need whatsoever of looking at what kind of damping. You just assume it in this particular case. Do you understand that? Okay. I am going to stop over here for today, because this entire discussion was on how to consider damping in multi-degree of freedom system problems. I hope I have been able to get across the point of how to consider. But again, at the end I said that, look, it is not relevant, because if you are using a linear system and mode superposition, you define xi to be the same in all the modes and just solve the problem. That is all. You save 5% damping. So, 5% damping in all the modes. You consider, solve it and go ahead with it. Okay? So, I hope I have been able to explain a little bit of how to consider damping for multi-degree of freedom systems. From next time onwards, I shall look at the specific case of earthquake loading. Thank you very much. See you next time. Bye.